Welcome back for Algebra 2 lessons. We are talking about number sets today, and this is a really important base that we're going to use for the rest of the year. So we're going to talk about types of numbers, but we are also going to talk about notation, and it's really important that we understand that notation. So a set is a collection of items called elements. Whenever we have a subset, it's a set of elements who belong to another set. So a subset is a smaller group that belong to another set. The empty set is denoted with empty brackets, or you can also denote it with this, which stands for the null set. So we're going to talk about the real number system. The only thing that's not real are imaginary numbers. And we're not going to work with imaginary numbers till later in the year. So everything that we work with will be considered real. So we have our real numbers, pretend this is one note card, and then on a note card right beside it, we'd have a whole separate issue, and that would be imaginary numbers. All right, so looking at this, we want to fill this out. And so this real numbers, everything here belongs to it. So I'm going to go ahead and define these down here, and then we're going to come up and write some examples. So we're going to come back to this graphic organizer. So real numbers can be written as a symbol. It's a double-lined R. That denotes real numbers, which are all rational and irrational numbers. So all rational and irrational numbers. So let's come back up here. The real numbers we can denote with a double-lined R. Now you are not required to know the symbol. However, if you don't want to write out real numbers, you can use a symbol. Sometimes answer keys have the symbol, so it's good to have this on your notes. So real numbers are rational or irrational numbers. So all of these are subsets of the real number system. And so let's talk about rational and irrational numbers. I'm going to jump the whole way down here. So rational numbers are denoted with a Q, and it's a double-lined Q. So double lines on that tick. And it can be, rational numbers can be expressed as a quotient, can be expressed as a quotient of two integers, which is really a fraction. Okay, a quotient of two integers is a fraction, like 1/2. It can be where the denominator cannot be 0, so it can be a fraction where denominator is not 0 because we cannot divide by 0. It can also be a decimal that terminates or repeats. Decimal that terminates, meaning it ends, or repeats. So some examples of rational numbers. 0.5 is a rational number. It's a decimal that terminates. It can also be written as a fraction. Any decimal that terminates or repeats can be written as a fraction. All right, it could be something like 2 7/9. It could be 6.71298. As long as it ends, it is rational. I'll put our double-lined Q up here. That is the symbol. And I could have something like 2/3, because 2/3 is actually 0.6 repeating. And we round it to 0.67, but it's really repeating. We can also have a perfect square underneath the square root sign, because the square root of 25 is 5. So all of these are examples of rational numbers. Now, let's contrast that with irrational numbers. Irrational numbers cannot be expressed, and there's no symbol for irrational numbers. So I'm okay if you want to abbreviate it as IRRAT, but there is no symbol for irrational numbers. So irrational numbers cannot be expressed. So it's really the inverse of a rational number. They cannot be expressed as a quotient, meaning no fractions. So they cannot be expressed as a quotient of two integers, two numbers. And we'll talk about integers in a minute here. The decimals do not repeat or terminate. Decimals do not repeat, so do not repeat or terminate. So basically, an irrational number keeps going on. So if I look for irrational numbers, again, the abbreviation, if you want, I would at least write that out. If you write out an I, that gets confused with integers. So irrational is what we have here. So the first example that comes to mind is pi. We abbreviate pi, we round it to 3.14, but pi is not rational. There is no end, it does not terminate. So pi is an irrational number. Anything that is not a perfect square underneath the square root is irrational. The square root of 2 is not a perfect square. So if I get my calculator out and I throw in the square root of 2, it looks like it terminates, but my calculator only gives me so many decimal places. And some of you have other calculators and they're maybe set to only give 4 decimal places or 5 decimal places. So it might look like it terminates, but I can tell you that anything that's not a perfect square is irrational when you take the square root of it. So we might round this to 1.4, but we have rounded it. So that is an example of an irrational number. All right, other ones. I could have something like the square root of 3 over 7. I could have -5 square root of 3. As long as there's an irrational number, times it, divided by it, it's going to be irrational. E is something we'll talk about later when we talk about natural logarithms. That is also an irrational number. All right, so we've got real numbers, and each real number is either rational or irrational. These are subsets of real numbers. And so we're going to start breaking it down into these smaller circles. So we're going to go with the next biggest thing, which are integers. Now, the symbol for integers is a Z, and again, it's a double line Z. That's the symbol for integers, so I'm going to throw that in there. And I'm going to put the word integers in here. Now, integers are positive or negative whole numbers. That's the definition. Positive or negative whole numbers. So in order to know what an integer is, you need to know what a whole number is. But let me show you. So I'm going to use roster notation, and I'm going to show you that it would continue into infinity, down in the negatives, -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. So the idea is you have positive whole numbers. Oh, I forgot my 2. Let me try that again. 2, 3. There we go. That's better. The dot, dot, dot shows that that pattern continues. So the idea here is you've got positive numbers, you've got negative numbers, but notice there's no decimals. No fractions, no decimals. That's a whole number, okay? So integers, positive or negative whole numbers. So if I wanted to give some examples, I would probably just squeeze that in here. -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. So no decimals here. So if I'm looking here, none of these, 2/3, 0.6, none of those are integers, but the square root of 25 would be considered an integer. Okay, so let's go ahead and officially define whole numbers. And yes, this is I. It's integers. So we don't use I for the symbol. We don't use I for irrational. It's a double line Z. Again, you don't have to know that notation. You can just write in the word integers. Whole numbers, this one makes sense. It is a double-lined W, just like that. That's the symbol for whole numbers. Whole numbers, the best way to describe it is to just list them. They start at 0, 1, 2, 3, dot, dot, dot. That's your whole numbers. So here's how I remember it. Whole numbers start with a whole, which is 0. Okay? So whole number starts at 0, 1, 2, 3. No decimals or fraction parts. Everything is a nice whole number, but it starts at 0. So whole numbers go here. And again, the symbol is a double-lined W. And so we'll just put the set in there. 0, 1, 2, 3, dot, dot, dot. What I need you to remember is that all of these there's infinite numbers here because we have infinite whole numbers. We never stop counting. All right. So if you look at this, whole numbers are a subset of integers because whole numbers are this part of the integers going up, but we don't have any of the negatives included in whole numbers. Now, natural numbers takes it down one more step, and we use an N for the symbol for natural numbers, and the natural numbers start at 1. The other term you might see for natural numbers is counting numbers. So I'm going to say or counting numbers. So it is natural to start counting at 1. When you're little and you start learning your numbers, you count 1, 2, 3. And so that's the only difference between natural numbers and whole numbers. Whole numbers have a 0, natural numbers don't. They both have infinite numbers in them, but that doesn't have a 0. So that means natural numbers come down here. So natural numbers are here. Double line that N, that's the symbol. And 1, 2, 3, so no negatives, no decimals, that's it. Okay? So you can see that the natural numbers are a subset of the whole numbers, which are a subset of integers, a subset of rational, which is a subset of real. And I also want to remind you that it is either rational or irrational. If your number is irrational, that is it. There are no further subsets for us. All right, so this would be a great thing to transfer to a note card or a separate graphic organizer. That way you have notes to look back at. It's really important that you can classify these. So we have an example down here, and it says consider these numbers. We're going to order them from least to greatest. Seems like a simple task, but here's what I know. 0.6 repeating would really be 0.6666, and it's going to keep going with that repeating. And the reason I want to write that out is because what if another one was 0.65? I have to consider which one's greater. Now, the square root of 2, I'm going to throw that back in the calculator. It's 1.41, so I'm going to write that above it. And we know that this goes on forever. Negative 5/2 is the same as negative 2.5, and then we've got this decimal. So I think it's really important when you're putting numbers in order from least to greatest that you look at what the number is. So the smallest number is my negative, and you always give the number back as an answer in the form it was given to you. So I just did the negative 2.5 so I could place it, but I want to come back to the negative 5/2. The next smallest number is 0. Don't skip that. All right, the next smallest number, I go between these two, and it's 0.5129. So I'll list that, 0.5129. All right, the next number would be 0.6 repeating because that is already greater than 1. So I would write this at 0.6 repeating, and the last number I fill back in as a square root of 2. This should be a simple task. It should be a freebie, but you want to take your time. You also want to double check how many numbers you have and how many you put. I always have some students who skip some of those. Okay, let's keep going here. We are going to work on classifying numbers. So I'm already on the back of my paper, and my classification chart is gone. This is where it'd be really nice to have a note card. I have an extra copy of it here, so we're going to use this to help us, but it is going to be on you to know these terms. And in this chart, I'm giving you the names, but on a test or a quiz, it will be on you to know all of the names. So you won't have a word bank. 2.3, repeating. It's absolutely real. All of these numbers are real. None of them are imaginary. We'll talk about that later. No tricks here. Is it rational or irrational? So these pair up together. 2.3 is a repeating number, and rational numbers can repeat. We know what happens. So it is considered rational. But because of that decimal, it's not an integer. And if it's not an integer, it cannot be whole or natural. All right, so pi. Yes, that is real, but pi goes on forever. It is irrational, so there is nothing in between. All right, we've got the square root of 5. Well, the square root of 5 is not a perfect square, but let's say it was a bigger number and I wasn't sure of it. Anytime I'm not sure, I might as well throw it in the calculator, and I see it's not a perfect square. So I know that it's real, but it's also irrational. 2.7652, okay, that ends, it terminates. So it's real and it's rational. Now, just to show you, if I would have changed this to 2.7652, now that is rational because it terminates, But if I put that little dot, dot, dot on it, it now becomes irrational. So that dot, dot, dot tells us this number goes on, and we've cut it off. So be careful. That's all the difference it takes. So that's rational because it terminates. But the minute I put a dot, 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 that is now real and irrational. Okay. Negative 11 over 2. Well, it's written as a fraction, so it is rational. But before I say that's it, I want to think about what negative 11 over 2 is, which is negative 5.5. So it is not an integer because of that decimal. All right, so here is a try this. This is a great place to pause your video and you fill in the chart, and then we will come back and go over it. All right, so this is a terminating decimal. It is real, it is rational, and that is it. The square root of 2 was one of our examples. It is real, but it is irrational. 0, ooh, here's one. It's real, it's rational. 0 is also one of my integers, positive or negative whole numbers, and 0 is the smallest whole number. But the smallest natural number is 1, so 0 is not a natural number. 24, it is real, it is rational. It is a positive integer because it's a whole number. It's also included in the natural. All right, negative 5 over 2 is real. It's written as a fraction. Its decimal is negative 2.5. So because it has a decimal, it doesn't divide evenly. It's not an integer, whole number, or natural. If I had something like 10 over 2, then you look at it as a number. So let's do that real quick. Let's do negative 10 over 2. Well, that equals negative 5. So that is real, it's rational, but because it simplifies, it is an integer. But it's negative, so it's not whole and it's not natural. Okay, so here's where we get into some heavier things that a lot of you haven't seen before. And so we want to make sure that we take the time and wrap our head around it. We will be using these different notations throughout the year, and you'll normally use them in higher level math classes too. So take a deep breath, it's something new, and we're going to work through it together. There are many ways to represent sets. Words are one way to describe a set. So if we're talking about words, that's easy. We just say natural numbers, all right? But another way is called roster notation. Just like a list. So a class list, a batting order, a team list, a roster. So the elements of a set are listed between braces. I call them fancy brackets. So that's how we list them. So when we did our notes over here, this is examples of roster notation. This is an example of using words to describe it. Okay, so roster notation is going to be a list. Now, we can have finite or infinite sets. So a set is finite, and that's like the set of billiard ball numbers. Okay, we can count how many billiard ball numbers there are. We can count how many digits there are, 0 through 9. That's finite. Infinite are the natural numbers because we start at 1, but then they keep going. There is no end. So a finite set has definite finite number of elements. We can count them. An infinite set is unlimited. I can represent roster notation with a finite or infinite set as long as it's discrete. And we'll be talking about that more. Okay, interval is what we're going to use a lot of this year, and that's what's really new to you guys, is interval notation. So interval is a set of all numbers between two endpoints, such as 3 and 5. Okay, I want you to think about that. It's all numbers between 3 and 5. So if I ask you that, all numbers between 3 and 5. So I'm going to say it again. All numbers. Between. All numbers. That's another key word. Between 3 and 5. So some of you are out there thinking, okay, all the numbers between 3 and 5. 4. Those are all the numbers between 3 and 5. And someone else was like thinking, oh, well, 3, 4, and 5. Well, if it said from 3 to 5, yep, 3, 4, 5. If it said between, it's 4. But all of these are wrong because it says all numbers. If it said integers, whole numbers, natural numbers between 3 and 5, then you'd be saying 4. Because with a whole number, there's no decimals. When they say all numbers between 3 and 5, think about that on a number line. 2, 3, 4, 5, 6. All numbers between mean not included. So I'd have an open circle to an open circle, and I'd shade everything between. You guys know that. You've been doing that for a long time. So what am I talking about? 3.1 is a number between 3 and 5. 3.00001 is a number between 3 and 5. 3.11. We could be here all day just doing 3 point something, not even getting 3.2. There are infinite numbers between 3 and 3.1. There are infinite numbers between 3 and 5. 4, 4.1, 4.2, 4.21, 4.201. We could be here forever, literally. So all numbers between 3 and 5 means everything. That is infinite. So yes, it starts and stops, but there's infinite things between here. So I could not list this in roster notation. I have to list it in interval notation. So interval notation almost looks like an ordered pair. So in interval notation, I would use parentheses and say it goes from 3 to 5 because it says between. If it said from 3 to 5, when I go to graph it, 3, 4, 5, I would use closed circles. That's what we always did. We would use closed circles and shade it. And how I do it is I go bracket 3 to 5 bracket. So it just looks like I made a typo if I was typing this. So let's back this up. We're used to the open and closed circles, greater than, less than, greater than or equal to, less than. But now we're going to change it up to brackets and parentheses. So here it is. The symbols with a bracket, close the bracket, sorry for the bells. These brackets, the brackets include the endpoints in the interval. If we have parentheses, the symbols, parentheses, and the other one, to close it, exclude. They exclude the endpoint. From the interval. Now, we'll take it a step further. Instead of using open and closed circles when we graph it, we would actually graph it parenthesis to parenthesis, bracket to bracket. And so it streamlines it. There's no inequality here. We've taken it from 3 is less than x, which is less than 5, to 3 to 5. It does look like an ordered pair. So interval notation is one we're going to use a lot. Put a little star beside that. So let's go ahead and take some time and practice this. So we have methods of representing intervals. And so we're going to take some time and talk about this. In words, numbers less than 3. Okay, let's think about that on a number line. Numbers less than 3. And I want to point out that it says numbers. That means any real number. Rational, irrational, infinite numbers. So I'll put a couple numbers on here. You always need more than what you have. So a number line should be evenly spaced. And it says less than, so not including. So open circle at 3. And less than would shade to the left. So that's what my number line looks like. It helps me wrap my head around it. As an inequality, I would write x is less than 3. How do I write this in interval notation? Okay, interval notation always goes from low, comma, high. And then you would either have a bracket or a parenthesis, depending on what we're talking about. Now here's the deal. There is no low. This goes forever to the left. There is no low. So the low would be negative infinity. All right. The high stops at 3 and it's not included. So notice I put a parenthesis here. We can never reach infinity. So that would be a parenthesis. So with this example, I want to take a minute and I want to go back to our prior page of notes and I want to add that information in. So I was talking about interval notation. In interval notation, we include negative infinity and positive infinity if it continues to the left, and positive infinity if it includes to the right. You do have to use the negative symbol to show that it's negative infinity. The positive infinity symbol is understood. You don't need the positive sign there. Anytime you do infinity, you will always use parentheses, because the brackets mean that it can equal that, will never equal infinity. So that's why it's always parentheses. Now, one of the common mistakes on this example is that a lot of people will write it from 3 to negative infinity, because they're looking saying, well, 3 is the number and then it goes here. This would be wrong because it always has to go from low to high. So envisioning it on a number line is really helpful. All right, so next problem here. We are going to do numbers greater than or equal to. So since it's greater than or equal to, it would be a closed circle. So let's sketch another number line here. I always like to go a little below and a little above what we're focusing on. And so I would put a closed circle on -2, and greater than would shade to the right. So if you are doing a number line, you want to make sure that it's clear where your shading is, make sure it's clear that it's open or closed, and to be proper, you shade that arrow to show that it continues forever. So how do I write this as an inequality? The x value is greater than or equal to -2. All right, so looking at this number line, that's my interval notation. It starts at -2, and it can include it because it's equal to, and it goes to positive infinity. So if we can compare what we did in interval notation, it is exactly coming from that number line. And then you might see a number line where instead of having a closed circle, you have a bracket replacing that, or a parenthesis replacing that. All right, now notice it says numbers between 2 and 4. So it's not including 2 and 4. So 1, 2, 3, 4, we'll go to 5. All right, so numbers between would not include. So open circle to open circle, shade in between. And that would be 2 is the low, 4 is the high, x is in between there. Now I'm going to write this as a compound inequality. So 2 is less than x, which is less than 4. This is an and statement. 2 is less than x, and x is less than 4. If you read it from this way, x is greater than 2. The x value is bigger than 2. You have to have these being the same way, and if I covered up the x, 2 should be less than 4. All of it needs to be true. So in this one, interval notation, the low is 2, the high is 4, and they're both not included, so we have parentheses. All right, now it says numbers 1 through 3. So 1 through 3, or from 1 to 3, would include it. So 0, 1, 2, 3, 4. We would have closed circles on 1, closed circle on 3, and then shade everything in between. And so here 1 is the low, 3 is the high. And so this time 1 is less than or equal to x, and x is less than or equal to 3. Again, if I cover up the x, the sign should be the same way, and then 1 should be less than or equal to 3. Now, this, again, low to high, but both are included, so it would be a bracket. There are times that you might have one bracket and one parenthesis, and that's fine. So just give you a quick example. If I showed you 1, 2, 3, we'll go 0. And 0 has an open circle and 3 has a closed circle. That would be that 0 is less than x, which is less than or equal to 3. So my interval notation would not include the 0, but it would include the 3. So you might have a mix. All right, so here is an inequality, and we're asking to use interval notation to represent it. So there are infinite numbers between 7 and 12, but it includes 12. So the low, 7, the high is 12. This has a parenthesis because it'd be an open circle, and that has a bracket. And that is what your interval notation looks like. All right, now we have two things going on here. So x is less than or equal to 2. So if you think about a number line, 2, 4, 6, I'm going to count 8, 10, 12. There we go. So if we look at a number line, x is less than or equal to 2 would be a closed circle, and we would shade going this way. but then it jumps and it says 3, so open circle at 3, and it goes up to 11 and it includes it. So here I have 2 intervals, which means I need 2 things for interval notation. So we start from the low. The lowest it can go is negative infinity with a parenthesis. It stops at 2 and it includes it. You use a union symbol, which is really the word or. So union represents the word or. So there's that word or, where this was an and statement. And then we jump. And so it could be from 3 to 11. It does not include the 3, but it does include the 11. So this is a little bit different. So union symbol or the word you, and there's your interval notation. Okay, so another way, so we've got roster notation, we've got interval notation. Roster is the list, interval is the brackets and parentheses, low to high. And another way to do it is called set builder notation, which is pretty forgiving. So we have set builder notation. With set builder notation, it uses the properties of elements in the set to define the set. So we can use words, we can use inequalities, and that symbol right here, that sideways C with a line through it, looks like an E, that's the element symbol. So let's talk about a couple here. We want to represent these in different ways. It says all real numbers except 1. This is not possible, so non-applicable. You cannot list all the real numbers except 1 because they're real numbers. So all the decimals are included here. So you cannot do it in roster notation. Now, in interval notation, all the real numbers except 1. If you can think about this, it means if you had a number line and the number 1 was right here, you would have an open circle and you'd shade below and you'd shade above. So it jumps over 1. So we would go from negative infinity up to 1, but don't include it, union 1 to positive infinity. So this gives us that 0.999, as close as we can get to 1, and this gives us that over on the other side of 1. In set builder notation, you would put a bracket, x bar, x cannot equal 1. Now let's talk about that real quick. In set builder notation, it starts out with a bracket, x such that, and then you fill it in. So that's what that stands for, x such that this is true. So you're defining your variable, I have x, and this is what's true about x. With set builder notation, we could do that, or we could have actually said x such that, and we could have just written this exact same thing right here. All right, positive odd numbers. There are infinite positive odd numbers, but I can do it in roster notation. If I would write the odd numbers, that should be a 3. 1, 3, 5, 7, and then that pattern keeps going, so I'm just going to go dot, dot, dot. Interval notation, I cannot do that because this is considered discrete. There are infinite positive odd numbers, but there is nothing between 1 and 3. And when you do interval notation, we're talking about infinite numbers between two things, not discrete. Set builder notation, honestly, I'd probably write x, that x is a positive odd number. You could have worded it as positive, or you could have worded it as odd whole numbers, all right? Or odd integer, or odd natural numbers. Okay, so there's ways to word that. Now, the way the textbook worded this one is a little bit different. They actually went in and they did a formula. So this is a little higher level thinking. X such that x equals 2n minus 1, and n is an element of the natural numbers. So that is another way you could do it. So how do they get this 2n minus 1? If you double any number, it will be even. So double the number, take away 1. And then it says n has to be an element of the natural numbers. So n cannot be 0. N has to be 1 or 2 or 3. So anything I double and take away 1 will make it odd. So that's why set builder notation is a little forgiving. I can do it in words, I can do it with symbols, I can do it with equations, but I had to define a little bit more. Okay, now, numbers within 3 units of 2. Okay, what are they talking about? Numbers within 3 units of 2. So let me wrap my head around this. Here's the number 2. If I go above 3 units, I get to 5. If I go below 3 units, I get to -1. So that's the idea, almost like the absolute value, 3 above, 3 below. So if I'm talking about numbers within meaning including it, I cannot put that in roster notation because it's not just -1, 0, 1, and 2. They are any number, not integers, any number. If I said integers, then we could list them. All right, now, since it says within 3 units of 2, I can include both of the endpoints. So that's what I have there. So -1's the low, 5 is the high, bracket on both because they're included. Set builder notation, bracket x such that -1 is less than or equal to x, which is less than or equal to 5. So I just put in a compound inequality. Okay, so this is where you might want to pause the video and give these problems a try. So we're given the different notations. We want to rewrite in the indicated. So I have the numbers 2, 4, 6, and 8. We want to put it in words. So there's lots of ways of doing it. I might say even numbers. So I'm defining them as even, but it's not all even numbers. It's even numbers between 1 and 9. Someone else might have worded it even numbers from 2 through 8. And that word from means including. All right, this one, x, this is in set builder, so that was roster. This is set builder. X such that 2 is less than x, which is less than 8, and x is a natural number. Okay, if this wasn't here, there are infinite numbers between 2 and 8, 2.1, 2.01. I could not do roster notation. But because it's a set of the natural numbers, 1, 2, 3, 4, 5, and so on, I can do roster notation. Now, notice the 2 is not included. So the next natural number is 3, 4, 5, 6, 7, and 8's not included, so that is it. Okay, we have interval notation. So this is given in interval notation, and they're asking us to go to set builder. If you think about this on a graph, you would start at 99, and it would be a closed circle because it's included, and then you would shade going above. All right, so with that in mind, we're going to put this in set builder, and it would be something like x such that x is greater than or equal to 99. And so I can throw an inequality in set builder, or I could have put it in words. All right, last idea, numbers and symbols on a telephone keypad, put them in roster notation. So if you think about a telephone or a calculator, you only have 10 digits, 0 through 9. So we would list that, the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But you also said symbols on a keypad too, and the symbols are pounds, which you know is hashtag, and star or asterisk. And that is your set. All right, make sure you're practicing this, and we will continue work.